Welcome to the course on Introduction to Electrical Engineering. We will have a lecture 25 Digital Circuit part 1 today. We will start from digital circuit. First, we will like to discuss number system, and we have a many number system like binary numbers, then decimal numbers, octal numbers, hexadecimal numbers, and then we will talk about conversion from one number system to another number system. Even among them, there are maybe many other, but we will like to discuss which are quite frequently used in the day to day life or even in computers. Then we will talk about this typically codes, binary coded decimal number is in short called BCD or gray code, then we call it XS3 code, and of course, alphanumeric code. Then we will talk about complement system, which are used for the many arithmetic situation in binary number, and of course, we will talk about exercises and numerical problems followed by references. So, coming to the first part of introduction for this digital circuit or digital system. So, we will talk about what is the application of this digital like a system, or first is the computer. You just see a whole day, whether it is a laptop or desktop, as you can see the photograph, we use the digital numbers into that. Then digital technology, which are going to be now digital drone. You might have heard about a lot of news about drone. So, we use the entire digital system only in that. Then digital technology and digital television. So, most of the things are coming now, you can say a digital form like then digital technology for digital watches. You can see the how it looks like a digital watch from inside as well as from outside. Then typically in your digital calculator, and of course, internal PCB of the this digital calculator. Then the geolocation technology, from which you can probably put location with the mobile. Like you just look into the location and you can even predict the distances and many things. So, it is used virtually for this geolocation used for many purpose. So, it is also as a outcome of digital technology. Then the robotics, we control the robots with the help of this entire digital system only or digital technology, or that ATM, this is also used by digital technology. Then the code scanner machines, from which you identify the particular item. You might have gone many of the mall or the shops where the or even the many you can call it most of the item, how they are identified by the code, and you have a scanner machine that can decode the entire information of that product or that item, which you are putting from this your typically this your typically of code message like. Then the video streaming, that is also used for typical by in digital technology, or smartphones use again digital technology. So, now coming up typically what really inside of all these applications, like how it goes the digital technology inside of these systems like So, in case of as a fundamental approach or basic approach of it. So, we have a like a numerical representation. There are two ways of representing the numerical numbers. One is the analog, and quantity are represented by continuously varying variable, which is a proportional indicator and can vary over a continuous range of values like real numbers, that we call it like a analog numbers or analog quantities. We will give you some example of that. The another is the digital quantities, which are represented by continuous variable indicators by the symbols called digits, and changes in discrete step like integer values or so. So, this we call it digital numbers like or analog quantity or digital quantities like. Typical example here you might have seen that typically your speedometer in your vehicle, whether it is your two-wheeler, three-wheeler, four-wheeler. So, you have analog representation of your typically your meter speedometer there, and you have a now digital representation. So, it give you digital number typically. So, of course, in many meters you probably may find in the one itself both like. So, that is analog and give idea to you what is the analog representation, what is the digital representation. So, then another is like a thermometer. So, you have a thermometer like a digital number is visible here, like you can see the digit 98.6, and you can see the typically a thermometer where you have to read the in between the scale what is the temperature, I mean typically on analog form. Then you have analog representation of your clock as well as digital representation of the clock, like as you can see the digits. Then you have again the voltmeter, I mean above one is the analog version, lower one is the digital version. So, you can by this time you can discriminate between what is the difference between digital and analog quantities like. So, digital systems are generally easier to design, and exact value of voltage and current are not important in digital system, and information storage is very easy of digital system or digital numbers, and mass storage technique that can store billions of bits of information in a relatively small physical space, and that is we have a flash drive. Of course, analog storage capability are by contrast extremely limited. So, well, the accuracy and precision are all easy to maintain throughout the system, and now it does not affect the information in digital system too much as it being processed, easier to keep track of integer than the exact real number. More digital circuitry can be fabricated on IC chip. Analog system have not achieved the same high degree of integration, and of course, the operations or computation can be programmed in case of digital technology, and it is fairly easy to design digital system whose operation is controlled by a set of stored instructions like integer manipulation called a program, and digital circuit are less affected by the noise, and since the exact value of voltage or current is not important, round of error can be tolerated. So, of course, there are some limitations or drawback of digital techniques. So, real world is analog, physical quantity have real values, and the input have to be converted from analog to digital quantity using analog to digital converters, and the output have to be converted from digital to analog quantity using a digital to analog converter to give the signal, of course, maybe in many time to the physical system for actuation or for the purpose of control, like well, most of the system work physical system work on analog quantities like or analog form like. So, the processing digitized signal can thus take more time, and there are specific situations where use of analog techniques is faster, simpler and more economical. The typical example analog to digital signal, I mean you can just see how analog signal is your red signal which continuously changing like a kind of looks like a sine wave, but the digital number is discretized system, maybe in that equivalent to a decimal number, you can see how the level are changing. So, they can be only in digital form with the discretized form like. So, you can just have idea how the digital number and how analog quantity or the quantity in the digital can be represented like or can be even converted equivalent to. Then you can see again analog to digital system in binary form. So, you can clearly see, I mean that was in decimal, here it is analog quantity you can clearly see, and the equivalent binary number is the representation you can clearly see here. Then you have a number system, I mean number system which used in digital system either for design or for handling the total digital system. So, we have a of course, the number system unweighted number or weighted number and no position weight or positional weight. The typical example of unweighted numbers is like gray code, XS3 code. However, for weighted number is like a binary, decimal, octal and hexadecimal, where the location decides the typically the weight of the number like of digit or so. So, the many number systems are in use in digital technology, and the most common are the decimal, binary and hexadecimal system, and number system with the base r will have a r different digit, and they are from 0 to r minus 1. So, typical example is here is we have a binary where base is 2. Base 2 means we can represent the binary number virtually in 2 form only, and which have a typically like as written 0 r minus 1 for r digit, typically r base r. So, here it is 0 1 for binary number, and for octal of course, there are 8, you can call it like a you have a base value of 8, and it can have a total 8 kind of digits, the 8 different digits, and which goes from 0, 1, 2, 3, 4, 5, 6, 7. Those 8 distinct digits are used for this octal number. Similarly, decimal, I mean total base value is 10. So, there are 10 quantity which goes from 0 to 10 minus 1, that is 0 to 9. So, 0, 1, 2, 3, 4, 6, 7, 8, 9, and then we have hexadecimal where the base is 16. So, we have a typically 0 to 16 symbol. So, here 0 to 9 taken from decimal, and for starting from 10 to 15 we represent by A, B, C, D, E, F. So, F represents the here the 15, typically, and tetra is a 4. So, we have only 0 to 1, 3, that is 4 minus 1 like. So, this is how the digits are there in your typically number system with having the base R. So, usually of course, we are dealing most of the time either binary in the computer and of course, decimal in day to day life. Of course, we deal some time when the hexadecimal also in some of the system. So, we will talk about all the number system like more detail. So, of course, when we talk about the first as a binary one, we will discuss why binary one. So, there is a terminology which called bytes. A bytes always consists of 8 bits, and it can represent any numerous type of data or information. Nibbles, in the early days, the digital of a digital system, a term caught on a describe a group of 4 bits, and because it is half as big as byte, so it was named as nibble. Word, a word is a group of bits that represents a certain unit of information, and size of the word depends on the size of the data pathway in the system that uses the information. And now, first starting decimal system, because you have been and have grown so far dealing with the decimal system for all the day to day life work like. So, the digital number system, as far as decimal system is concerned, the word digit is derived from the Latin word for finger, and as the people have 10 fingers. So, we have a 10 digit in decimal number. So, decimal system is composed of 10 numerals or symbols, and these 10 symbols are from 0 to 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and using these symbols a digit of a number can express any quantity. It also called the base 10 system because it has a 10 digits. So, it is the positional value system in which the value of a digit depends on its position. So, various positions relative to the decimal point carries weights that can express as power of 10. Example is, consider the decimal number 453 or 453. In this digit, 4 represents the 400, 5 represents the 5 tenths, and 3 represents the 3 unit. So, that is the position you can call it in this number of 453. Now, consider the number 2745.214. It is equivalent, can be written as a 2 into 10 power 3, because it is a typically of 4th position, and 7 into 10 power 2, and 4 into 10 power 1, and 5 into 10 power 0, that is for integer part. Now, for a fraction part, we write it plus 2 to power 10 minus 1, that is for decimal place 1, to 1 into 10 power minus 2, that is decimal place 2, and plus 4 into 10 power minus 3, that is decimal place 3. So, you can call it here the position weights are like, we can say we have a decimal in between, and from right side we say 10 to power 0, 1, 10 to power 1, 10 to power 2, 10 to power 3. Here of course, in this case it is the most significant digit, that is with the weight of 10 to power minus 3, 10 to power 3. Similarly, on fraction part or decimal part, we have again 10 to power minus 1 for first digit, then second digit 10 to power minus 2 on the right side, and 10 to power minus 3 further on least, you can call it the LSD, we call it least significant digit, which have a minimum value. So, we have a concept here most significant value and the least significant value. So, right side is the most significant, left side the most significant, MSD and LSD we call them in short like. So, now coming to that is about decimal number, just to make a concept here. Now, we will be extending the same concept for other number system like a binary number system. So, this binary number system, the decimal number does not lend itself to convenient physical implementation in digital system. Otherwise, we could have taken even a decimal number, but that really cannot go as a part of physical system implementation. So, it is very difficult to design electronics equipment, so that it can work with the 10 different voltage levels, and it is very easy to design a simple accurate electronic circuit that can operate with only 2 voltage level that is like a transistor is on or off. I mean, so maybe on we can represent by 1 and off we can represent by 0. So, these are the two levels which can be easily taken for the binary number system like. So, in the binary system there are only two symbols or possible digit value are 0 and 1, and the binary system is a positional value system. So, each binary digit has a position value or weight expressed as a power of 2 and placed to the left of the binary point are positive powers of 2 and places on the right side are the negative power of 2, as we already discussed just few seconds about the decimal system like. Though the term binary digit is often abbreviated to the term bit, and the most significant MSB is the leftmost bit that called largest bit, and the least significant bit LSB is the rightmost bit called smallest bit like. So, the example is here typically like 1011.102 at the base of 2. So, we can say how the positional value are there. We have a binary point here which you can call it in between, and on the typically on the right side we have 101 and on the left side we have 1101, and their position value of course for right side it goes 2 to power 0, that is weight 1, 2 to power 1 that is 2, and 2 for equivalent decimal 2 to power 2 means that is 4, and for decimal equivalent 2 to power 3 that is equivalent to 8 for position value. That is most significant bit here. On the right side we have a 2 to power minus 1 that is half, 2 to power minus 2 that is 1 by 4, and 2 to power minus 2 1 by 8 that is equivalent to kind of decimal here. And you can call it like 4 cases can occur in adding the two binary digit bits in any position. We can say 0 plus 0 that is 0, 1 plus 0 equal to 1, and 1 plus 1 I mean can be like 1 0, or you can call it is 0 with carrying 1 into next position, or typically you can call it 1 plus 1 carry from previous that is 1 1, or 1 plus carry of the 1 into the next position. So, typical example adding here two numbers that is 1001 that is decimal equivalent 9, another number 1111 that is equivalent decimal 15. So, we if we add both here, I mean we can simply add like a 1 1 is added typical goes to the 0, then we have a carry 1 that goes another with another one. So, it also again becomes 0, 1 and 1 added, then carry goes 1, then again carry plus 1 is got added that goes again 0, and then we have a 1 carry and 1 1. So, it with 1 carry it becomes 1 here and 1 carry, and this comes as a 1 carry, and equivalent to of that if we convert into decimal this 11000 becomes 24, and 9 plus 15 is also 24. So, that is the way how really we add here also in the same manner as we do in case of decimal number. But of course, you can say is it another number system. So, it takes little time to understand how it is going to carry and how it is we take care for all the operations of like addition and other operations like. So, similarly, we have a binary subtraction or subtractor. So, 4 cases can occur in subtracting the two binary digit in any position 0 minus 0 that is 0, 1 minus 0 is like a positive 1, and 1 minus 1 is 0, and 0 minus 1 is 1 with the borrow from right side of 1 as we do in case of decimal number. But just to make understand with the example we can talk here subtract typically 1 1 0 0 1 1 that is equivalent to 27 decimal, and 0 1 1 0 1 that is equivalent to your 13 in decimal as it is shown here. And now, we can say how we will go ahead when we subtract upper quantity of 1 starting from least significant digit 1 minus 1 0, then second digit that is 1 minus 0 equal to 1, and then 0 1 0 minus 1 we have to carry 1, and then it becomes equivalent to typically 2 1. So, we subtract 1 and it comes 1, but next digit we have taken already carry. So, we take again carry from another one. So, it becomes again equivalent to 2 1 and we minus 1. So, 1 it becomes 1, and certainly you do not have next digit here. So, this 1 1 1 0 it becomes equivalent to 14, and that is certainly difference of 27 in decimal minus 13 is equivalent to 14. So, this is exactly similar to what we are going to have in decimal equivalent as far as addition and subtraction is concerned. Now, coming to octal number system. So, this octal system or with the base of 8, its octal means 8. So, it has a base of 8 and we have 8 digit to represent. Numbering system are commonly used to process large number through digital system, and as decimal number become larger, the corresponding binary number takes up more and more digit. So, alternate number system with base as sum of power of 2 are used. So, for example, the octal number has a 8 digit, that is 8 2 to power 3. So, it digit from 0 to 7, that is r minus 1. So, r is here 8 and then you have a 0 to 7 digit to represent this octal number. Now, the another number is a hexadecimal system or hexadecimal number. So, here the hexadecimal number system use base 16 and that is equivalent to 2 to power 4. Thus, it has a 16 possible digit system and uses digit 0 to through 9 plus the letters A, B, C, D, E, F. I mean up to 0 to 9 there are 10 digit, we need the typically 7 more digit and that we take 6 more digit, I mean from, because that is a 10 digit. So, 6 more digit comes from A, B, C, D, E, F. So, digital position are weight as power of 16. So, the letter A stand for a count of 10 for equivalent to decimal, and B stand for 11, C stand for 12 and D stand for 13, E stand 14 and F stand for 15, and the all that number of 16 goes 0 to 15. The advantage of hexadecimal system is its usefulness in converting directly from a 4-bit memory binary number. And now, coming to the conversion of number system, I mean from one type of number to another type of number. So, any binary number can be converted to its decimal equivalent simply by summing together the weight of the various position in the binary system by number, and that contains the digit 1. So, for example, to convert 1011 0101 from binary to decimal, so we keep just the typically first least most significant, that is 2 to power 0, that typically 1 in binary, then 2 to power 1, here it is typically 2 to power 2, 2 to power 3 0, 2 to power 4 is 1, 2 to power 1, again 2 to power 6 is 0, 2 to power 7 1. So, when you add these, I mean all 2 to power, it comes 181 at the 10 of base. So, this number is equivalent to 181 equivalent to a decimal number. To consider the binary number 1011.101, and if we represent it here, I mean as you can see on base 2 equivalent to a base 10. So, we say 1 into starting for most significant, that is the 4 digit. So, it comes 1 into 2 to power 3, then 0 to 2 to power 2 and 1 to 0 to power 1 and 1 to 0 to power 0, plus now on decimal side 2 to 1 to power 2 to power 0, sorry 1 2 to power minus 1, 0 2 to power minus 2 and 1 2 to power minus 3, and converting and adding equivalent to decimal them, it comes 11.625 at the base of 10. Or and here you can just see what we call it here in between, we have binary, and this digit of 2 to power minus 3 we call it LSB, least significant bit, and on the right, on the left side the most we call it this 2 to power 3 equivalent to a most significant bit, and we saw represent again you can call it MSB. So, now coming to binary to octal conversion. To convert a number from binary to octal, the binary number is grouped into 3 bits starting from right to most, and then each group is converted to equivalent octal digit, and 0 shown here shaded are added as needed to complete the 3 bit group. So, if you just see here convert this typically 1111 into octal number. So, this digits of this on base 2 we convert starting from right, we make a group of 3 bit, that is 111, then another 3 bit 111, and then remaining 2 bit are left, and but we have to make a group of 3. So, it comes with the 0. So, this as a group of 3, and now we can convert equivalent to a decimal of this. So, this comes 0 1 1 is 3, tuple 1 is 7, and tuple 1 is also 7, and that comes as a octal number 377 at the base of 8. So, that is the way how we convert this binary to octal equivalent like conversion. Now, converting binary to hexadecimal conversion, to convert a number from binary to hexadecimal, the binary number is grouped into group of 4 bits, as we did 3 bits in case of octal, starting from again rightmost or least significant bit, and each group is converted to equivalent hex digit. And typical example here, 0 shaded are added as needed to complete the 4 group. So, as you see here, the number starting from tuple 1 0, then 1 0 0 1 1 0, that is binary, and we start from this. So, we start from a group of 4. So, 0 1 1 0, first group of 4, then second group 0 1 1 0 1 0 1, that is second group of 4, and third group we left only 2, but on the left side we have to add 2 more zeros which does not change the value of the it, but to make a group of 4. And now we have here equivalent of it, the starting from here 0 1 1 0 is equivalent to 6, and here 1 0 1 0 is equivalent to A in hexadecimal, and 0 1 1 equivalent to 3 in hexadecimal. So, this number into equivalent to hexadecimal is 3A6 at the base of 16, that is a hexadecimal number. So, this is the way how we convert binary to hexadecimal number. Now, coming to binary decimal to binary conversion, we have a couple of methods here, 2 methods we have. So, starting from method 1, the decimal number is simply expressed as a sum of power of 2, and then 1 and zeros are written in the appropriate bit number, bit position. And for example, to convert 45 from decimal to binary, we take a 45 here, and typically we convert of course equivalent to starting from 1, then we add 4, then 8 and 32, and here the bit is starting from first 2 to the power 0, that is 1, then 2 to the power 1 is 0, there is no bit corresponding to 2 to the power 1, then we have a 4 that is equivalent to 2 to the power 2, that is we have 1 here, then 2 to the power 3, we have 8 here 1, and we do not have a 2 to the power 4, so that is 0, and we have a of course 32 to the power 5, that is 1. So, this comes at a base of 1 0 1 1 0 1 at the base of 2, that is binary number. So, note that 0 is the place in the 2 to the power 1 and 2 to the power 4 position, since all position must be accounted for when you convert from this your decimal to binary. So, that is method 1. It requires more logical one. The another method is method 2, the repeated division method, requiring repeated dividing decimal number by 2 and writing down the remainder after each division until a quotient of 0 is obtained. So, this looks to be more mathematical and logical one. So, the binary result is obtained by writing the first remainder as least significant bit, and the last remainder is the most significant, and all the other remainders in between in sequence like. So, until n bits, using n bits we can present the decimal number from 0 to n minus 1 to 2 to the power n minus 1, that is total 2 to the power n different numbers. So, now how it goes decimal to binary conversion? We start divide by 2, record a quotient and remainder, and is the quotient 0? No, we have to go back and repeat it, and if yes, collect R or remainder desired binary number with the first R as a LSB and last R remainder as MSB, and we end it. That is the method 2, repeated division by 2. And as an example, you can take here, we want to convert this binary, this example is convert 25 from decimal to binary representation. So, now what we are doing here, we are dividing 25 by 2. So, we say comes 12 as a full number, and then remainder is 1. This we take as a least significant bit, then 12 we divide by 2. So, it is 6 is the numerator and remainder is 0. So, we put a 0, then 6 we divide by 2. So, it is 3 the numerator, but remainder is 0, then 3 by 2 we have a 1 as a part of division, 1 remainder. So, it is 1, and then last one divide by 2, its remainder is 1, and your typically the numerator is 0. So, we end here because it has become 0, and this 25 to base 10 now becomes 1 1 0 0 1 to base 2. So, that is the method. I mean, one can program also in very systematic manner to convert this your decimal to binary number. Of course, it is little tedious, but once you develop algorithms, it does not take much time to convert in, and it comes very quickly automated manner with no problem by dividing 2. So, now coming to decimal to octal conversion, we follow the second method what we discuss in binary, that comes more simplified manner or logical manner. So, decimal to octal conversion can be done by using repeated division by 8, and then result is obtained writing the first remainder as the least significant bit and the last remainder as the most significant bit, and the all other remainders in between in sequence. So, convert 65 at the base of 10 into octal, and solution is here. We divide typically 65 by 8, the remainder comes 1, then we divide this 8 by 8, so it comes remainder 0, and now we write this in the sequence like 1 0 1 at the base of 8. So, that is how we convert decimal to octal. This is the same method as second method of what we use in for conversion from typically from decimal to binary one. So, it is a more methodological or mathematical one, the method we follow it like common or so. So, now going to be like a decimal to hex conversion can be done by using the repeated by division by 16. So, we convert 423 by 10 to hex. So, we 423 again we divide by 16. So, it comes as a 26 as a full number followed by remainder of 7. So, we write as remainder 7, that becomes the least significant bit. Again we divide 26 by 16. So, it is a 1 is the typically the numerator and remainder is 10. So, 10 is equivalent to here in hexadecimal equivalent to A, and then we divide this 1 by 16. So, there is no numerator full number integer and remainder is 1. So, this 423 at 423 at the base of 10 becomes 1A7 at the base of 16 into hexadecimal. So, that is the same method as second method of binary decimal to binary conversion. So, now octal to binary conversion, to convert octal number to binary number, replace each octal number by 3 digit binary equivalent. It is a very simplest form. So, for example, is 415, 8 each digit of your octal we represent equivalent to binary of 3. So, here you take a last most significant. So, 8 is 101 and 1 is 1001 and 4 is 100, and this becomes your 415 at the base of 8 becomes 100 001 and 101 at the base of 2 in binary. So, convert binary number into octal number, take the group of 3 binary digit starting from least significant and add the decimal equivalent here. So, again we are having this. So, we have a 3 3. So, we convert this first 3, second 3, third 3 equivalent to here, this becomes equivalent to 2 in octal, this becomes 7 in octal, and this becomes 2 in octal, it becomes 272 in the octal, and you can see that this require a quite less number of the bits as compared to you are having the bits in case of 9 bits or 8 bits in case of binary number, here only 3 bits are required. So, now coming to octal to decimal, a octal number can be converted to its decimal equivalent by using the fact that each octal digit position has a weight that is a power of 8. So, for example, convert 236 from octal to decimal. So, now we have a 236 at the base of 8. So, we write 2 into 8 to power is a third digit. So, it is a 2 into 8 to power 2 plus 3 8 to power 1 plus 6 into 8 to power 0, and when we convert equivalent it becomes 158 at the base of 10. So, conversion from any other base to decimal becomes quite straightforward. We just take that number equivalent to. So, now coming to octal to hexadecimal, write the equivalent binary number of octal combined and make the group of binary digit from right left each containing 4 digits and add the 0 on the left most left if there are less than 4 digit the group to find the hexa equivalent of each binary group. So, it is a method we take a binary in between. So, convert 7 4 5 6 8 into the hexadecimal number. So, convert this octal to binary and then binary to hexal. So, this we to convert this 7 4 5 6 octal into binary, just we have each of octal digit we convert into binary, like 6 is 110, then 5 is 101, and 4 is 100, and 7 is 111. So, this is in binary. Now, these were the group of 3. Now, we can make a group of 4, that is typically 1 1, 110, then 0 0 1 0, and 4 times 1, and now we can put equivalent to here. This 110 becomes E, then 0 0 1 0 is 2, and all 4 1 becomes F, and the number now becomes in hexadecimal F to E in a hexa number with the base of 16. So, that is the way how we can convert this octal to hexadecimal also. Now, coming to hexadecimal to binary conversion, to convert hexadecimal to binary, each hex digit is converted to equivalent to 4 bit binary equivalent. An example is 9 F 2 16 to binary. So, we have all three 9 F 2. So, convert equivalent to 4 digit like 0 0 1 2, then F is all 4 1, and 9 is 1 0 0 1, and we can write all these bits in with the base of 2. So, that is how we convert hexadecimal to binary conversion. And now, hexadecimal to decimal conversion. So, a hex number can be converted to its decimal by using the fact that hex digit position have a weight that of power of 16. So, here we have a decimal point. So, we can have a on the right side 10 to power 16 to power minus 1, 16 to power minus 2, 16 to power minus 3, and 16 to power minus 4, and right side left side we say 16 to power 0, 16 to power 1, 16 to power 2, 16 to power 3, and 16 to power 4. So, typical example here is 2 AF 6. So, we can have here just starting from 2 into 10 to power 6, 2 into 16 to power 2, then A is 10, 10 into 16 to power 1, and F, that is F is equivalent to 15 decimal into 16 to power 0, and this number becomes your 2 AF 16 becomes 687 at the base of 10, equivalent to decimal number. Now, hexadecimal to octal conversion. So, for each given hexadecimal digit, write the equivalent binary number, and if binary equivalents are less than 4 digit, then 0 are added on extremely left side, because that does not change the value of the number, and combine and make the group of binary digit from right to left, each containing 3 bits, and add 0 to the left if there are not as a combination are not less than 3 digit in last group. Now, find the octal equivalent of each binary group. So, example is here convert 1 BC 16 into a octal number. So, convert hexa to binary and then convert binary to octal. So, 1 B 16 we can convert C into 100, that is typically equivalent to 12, and then B, that is 1001, and 1 is your 0001. So, that is binary. Now, we can make a group of 3 starting from the your most right. So, it comes 100, 111, 110, and 000. So, this number comes your typically your 674 if we convert equivalent to at the base of 8, and this calls octal number. So, that is the way means this conversion we go through the binary conversion, it becomes very convenient to convert like also. So, now coming to the codes, these were the number system. Code we call it the binary coded decimal BCD code, and when number, letters or words are represented by a special group of symbol, they are being encoded, and the group of symbol is called a code. So, if each digit of the decimal number is represented by its binary equivalent, then the result is a coded called binary coded number. So, typically we have here typically 874. If we keep a equivalent to binary here, so we can, because in case of binary a number maximum number can be in case of decimal equivalent to binary as a 4 bit. So, we have to use the 4 bit of the your binary for each digit of decimal. So, it becomes 4 becomes 0 1 1 0, 7 becomes 0 1 1, and 8 becomes 1 0 0. So, this if we combine it, it becomes BCD code. Typically here. However, decimal to binary conversion we already discussed earlier, that is a different method. So, this is just like equivalent code, we call it the BCD code. Each digit of decimal we convert equivalent to 4 bit of binary number. So, BCD is not another number system like binary, decimal, and hexadecimal. It is just a code, and it is equivalent decimal system with each digit encoded to binary equivalent, a state binary number takes the complete decimal number and can represent it is in binary. So, BCD code converts each decimal digit to binary individually. So, that is we call it BCD, binary to coded decimal number. So, typical example here 137. So, we convert 7 into typically, then 1 and 3 all are represented equivalent to like a typically 4. So, 100, then typically you can say it is represented in equivalent to binary, and binary representation is done by, you can call it dividing by 2 by that we discussed it earlier, and then 13710 in BCD if we convert it, this is much different because 7 is converted 4 digit, then 3 also 4 digit and 1 is also 4 digit. So, these two are different. I mean this is binary, this is BCD. So, you can see these are not same equivalent in both. I mean 137 represented as a binary, that is different, and this as a represented this, I mean decimal to binary we just took in the same method as you write 137 by 2. So, it becomes 1 remainder. So, it remains like a 65, then like that we go on converting, which we discussed earlier like. So, now non-weighted gray code, in order to reduce the likelihood of a digital circuit misinterpreting a changing input, the gray code has been developed as a way to represent a sequence of numbers, and the unique aspect of the gray code is that only one bit ever changes between the two successive numbers in sequence, and it is used to encode data such as the shaft position of a motor or the physical location of a moving object. That becomes easier like. So, the MSB most significant bit of the gray code will be exactly equal to the first bit of a given binary number. So, you have a decimal here, you have a binary equivalent, and this is the gray code. And in gray code you can just see, you just have a, as it is mentioned here, the gray code will be exactly equal to the first bit of the given binary number like also. So, you can just see how, like, so method we will talk about. Now, take the exclusive of OR of MSB binary bit and with the next binary bit and so on. That is the method how we go it. So, XOR is the logic gate we already discussed earlier. So, if both, you can call it XOR will be if both two input are different, then only you will get 1. If both input are same, then you will get output 0. Like. So, that is the method you can just see here. If you take a first digit, you will get 0 here, then typically here first all will be 0, then last 2 bit if you that 1. Similarly, here first 2 0, then if you take a 0 1, that becomes 1 and 1 0 becomes 1 1. So, if you really take this method on this, you will find the quickly the result. For example, here the first is 1, okay, 0. So, you are getting 1 because it is a different, then next will be 1. So, first digit you are going to take same, and next you are taking the binary XOR of next to binary bit. Okay. So, MSB mostly of the gray code will be exactly equal to the first bit of the given binary number, that is exactly the same, and next bit will be of your exclusive OR of the two. So, here 1 is taken as it is, and next OR is a XOR of 1 0, that 1, and now XOR will be 0 0 will be 0, then XOR will be 0. So, that is when you can just look into carefully through exclusive OR gate, which we already discussed earlier. And typical conversion here 0 1 1 0 into gray code. So, you can say MSB we are taking as it is, that is typically 0, then we are taking XOR with the second bit, that is 1, and then 1 1 again same. So, it will be 0, then 1 0 again will be 1. So, this is the gray code of 0 1 1 will become 0 1 0 1 like also here. So, binary to gray code using XOR logic gate we use, that is the simplest method, comes as a conversion this from this to this like. So, MSB in gray code is always the same as the MSB bit we talk about, that is gray to binary conversion, and the next binary bit is found by comparing the binary bit of the left with the corresponding gray code bit XOR operation in the same manner here. So, you can just see typically here. So, example how it is going to be conversion to gray to binary code back, and this process repeated for the next with previous result in bit. And the typical example, convert gray code into binary code. So, you are coming here as a first gray code as it is 0, when you go to next you are already having 0 to 1. So, you have exclusive OR. So, you are having 1, then again from 1 to 0 you are going again, you have a 2 1 and 0. So, you will have a 1, and from now you are going to 1 1. So, both are input XOR gate output is 0. So, that is here 0. So, you will get a 1 1 0 1 0 1 0 1 gray code equivalent to 0 1 1 0. So, that is the same process we use as we convert for another one, again a exclusive method from gray code to binary or binary gate to gray code conversion. So, now net weighted access 3 code, a decimal code that has been used in some old computer in access 3 code, and this is unweighted code, and this code is obtained from the corresponding value of BCD after the addition of 3. So, access 3 code is BCD plus 0 0 1 1, that is equivalent to typically 3. So, that is the reason we call it access 3 code, and the access 3 code is a self complementary codes. So, you can have a here decimal number, you have a binary, you have a gray, you have a BCD, and you have a typically your here where you are adding, that is your access 3 code. So, in BCD code if you add 3, that will become your access 3 code as we discussed. So, this is just self complement or typically here as we are talking about how you are really going to convert from this to this or so. So, now coming to alphanumerical codes, the many application of digital computer require the handling of data that consists of not only the numbers, but also the also of letters. So, binary code must represent decimal numbers and some of the special characters, and alphanumeric sometime abbreviated alphanumeric code is the binary code of a group of elements consisting of a 10 decimal digit, the 26 letters of the alphabet, and a certain number special symbols such as your typically the a symbol of your dollar like. So, total number of elements in the alphanumeric group is greater than 36. Therefore, it must be coded with minimum of 6 bit 2 to power 6, that is 64, but 2 to power 5 32 will be insufficient like, because there are 36 like. So, you need the 2 to power 6 64 like. So, now coming to complementary system, complement system called complement number virtually. So, sign this is required for some of the mathematical operations of the binary number, we call it sign binary numbers. So, sign magnitude system, additional bit called the sign bit appended into the beginning to denote the sign of the binary number, and 0 is the sign bit represents a positive number, while 1 in the sign bit represents the negative number. So, you can just see here in this number of binary which is equivalent to a decimal of 52. So, this bit we call it the you can call it the most significant bit, we consider it equivalent to a sign number. So, we call this equivalent to a decimal plus 52 at the base of 10, and here it is sign bit is 1 which represents minus. So, again the number is 52 in decimal, that is minus 52 typically at base of 10. So, the most significant bit we take as a sign bit 0 or 1. So, 0 represents plus and 1 represents minus like. There is a reason for that we are going to discuss now. So, second complement system or second complement number system most commonly used. To understand it, we must need to define ones complement here. So, ones complement form obtained by changing each 0 to 1 and 1 to 0. So, example first complement of your 1 0 1 1 0 1 is just to complement it. So, 1 will become 0 and 0 will become 1. So, number becomes 0 1 0 0 1 0. So, typical example here 1 becomes 0, 0 become 1, 1 becomes 0 and 1 become again 0 and 0 1 and 1 to 0. So, this is original number and this is the first complement form of this number. So, it is so simple to understand the complement of binary number, just you can call it interchanging the bits only of the your binary number system. So, second complement form, the form by taking the ones complement of the number and adding 1 to the least significant position. An example, the second complement of this is your what is the 1 0 1 1 is 1 typically 0 0. So, what we do it here, we take a first complement, this is the number 1 0 1 1 0 1. So, the complement of its first complement is of it is 0 1 goes to 0 0 to 1 and 1 1 goes to 0 0 and 0 to 1 and 1 to 0, and now we add here 1 in this number. So, 1 become 1, then remaining bits remain the same. So, this we call it second complement of original binary system. So, it is also not very difficult to get the second complement also of this binary number. Just to take a just complement of all the bits plus add to least significant, and that becomes your second complement number of original binary number. So, now sign binary. So, second complement system, if the number is positive, the magnitude is represented is 2 binary form, and at the sign bit and a sign bit is 0 is placed in front of the MSB. So, you can just see here, I mean what we do here, we have a number 2 binary with the sign bit and we have a plus 45, and for second complement what we are doing, we are just taking all the complement here typically and adding 1 here, okay, that becomes second complement, and the sign bit we change into 0 to 1. So, this becomes your second complement number, that is minus 45 at the base of 10. So, this is the second complement, and we also change the sign also from 0 to 1. So, it becomes like a second complement becomes typically minus 45 or so. So, this is virtually to represent like a negative numbers. So, if the number is negative, the magnitude of is represented by second complement form, and sign bit is 1 placed in front of MSB here, as you can see here. To represent the plus 13 and minus 19 in second complement form. So, 13 here 1 0 0 1 in binary, and second complement of plus 13 is your typically I mean we are just taking complement of it. So, it will become you can call it 0 0 1 0, and we add into 1 here. So, it becomes typically this number, and then we have a sign bit here. So, to find out a representation for minus 9, we start from representation plus 9 including the sign bit, and then make the second complement. So, plus 9 is 1 0 with the sign bit, it is a 0 1 0 0 1, that is the 9 binary, and now first complement is just interchange all the bits. So, it becomes your 0 becomes 1, 1 becomes 0, and 0 0 becomes 1 1, and 1 becomes 0, plus we add 1 to least significant bit to convert to you can call it second complement. So, we add here, and this we are adding here typically. So, it becomes 1, then you have a again 1 1 0, then 1, and this we represent like a typically minus 1. So, this is second complement is virtually to represent the minus 9 of in place of plus 9 like. So, they become very interesting or simplified procedure to do the calculation in that way. So, now sign represented in second complement form, positive number loading 0 are added. Example, the 8 bit represented of plus 9 is your 0 0 0 and 1 0 0 1, and for negative number leading 1 is added. So, for example, 8 bit represented of minus 9 is you are just having here your the second complement of this 8 of 9 1 typically 1 0 0 1 1, and sign bit you added here, and then 6 extension to 8 bit format. So, this becomes your typical representation of minus 9. So, now coming to special case in second complement representation. So, whenever the signal sign number has a 1 in the sign bit and all zeros for the magnitude bits, decimal equivalent to minus is minus 2 to power n, and where n is the number of magnitude bits. So, for example, here 1 tuple 0 is minus 2 to power 3, and that is minus 8. So, we call it the complete range, that is for second complement equivalent to your can call it decimal equivalent. So, the when you are converting from second complement to decimal. So, complete range of values that can be presented in second complement system having a n magnitude bit is minus 2 n to power n to 2 to power n minus 1, and that is the total numbers becomes now 2 n to plus 1 number. So, now coming to the addition of the two complement system. So, first case is two positive number. If the same as normal binary system mentioned earlier as the second complement for a positive numbers is the same as the original binary representation. So, with 0 sign bit in 4. So, add 9 plus 4. So, this typically the 9 is 1 0 0, we are just adding here for positive number, and then typically 4 is 0 1 0 0, we are adding a sign bit here, and when we are adding all these numbers sign bit is still 0. So, we go this as a 1 0 0 1, it becomes 13. So, positive number addition is the similar way with the sign bit as we do normally in binary system. Now, coming to positive number and smaller negative number, I mean that is one positive one negative. So, both the number are written in second complement form and then added, and finally complement is this final carry is disregarded. The example, add 9 plus 4. So, we have a 4 as a in binary 0 1 1 0 1 0 0, and second complement is minus 4. It is we convert into first complement, I mean that becomes 0 1 1 0 1 1, then we add the 1 into to convert into second complement. So, it becomes by adding here it becomes 1 0 0, that becomes your typically the second complement, and then we have a sign extension here by adding 1. So, it becomes 1 1 1 0 0. So, the add typically the you can call it the 9 positive sign is 0 1 0 0 1, and the representation of minus 4 is here, it is with the sign bit of minus is 1, and the second complement what we discuss here it is already 1 1 0 0. So, now when we add together, so it be 1 0, then 1 carry over here 1, then you have a 0 here. So, you have a 0, and now you do not have a typically again you will have a carry and go to 1. So, this you can discard it because 0 has come here. So, this is discarded and the result is now 0 0 1 0, and that is the plus 5. So, that is the way it goes, very simple mathematical operations for even subtraction converted to the addition. Now, positive number and large negative number. So, both numbers are written in second complement form and they are added, and final answer is in second complement form as well. So, add minus 4 and plus 4. So, so second complement of 9 is here we can say the sign bit is 0 and the second complement is 0 1 1 1 of 9. So, then we have a 4 that is same 0 1 0 0, and then we typically add here. So, 1 1 and then go 0, then we come 1 and then 1. So, and this the sign bit, this is the 1 is the minus sign bit, and now this number becomes your, when we sum it is typically kind of fine, sum is minus 5. So, since the answer has a negative sign bit, the output is found by taking a second complement of the output number. So, the second complement of this number is you can call it like a 0 1 1 1 0 0 plus 1, that is your 0 0 1 0 1 equivalent to the 5 like also of this number. So, now two negative numbers, how we take a case 4 to consider as a 4, both are negative number, we want to add it. So, both numbers are written in second complement form and then added, the answer is second complement form as well, final carry discarded. So, here we have a 9 and minus 4. So, we have second complement of 9, that is typically 1 0 0 triple 1 and triple 1 0 0, that is for minus 4, and when we really add it here. So, it comes like 1 1 0 then 0 and typically 1 and then carry 1. So, this is your disregarded. So, number becomes 1 0 0 1, and this is typically now you can call it the minus 13 because we have a typically equivalent to. So, since the answer has a negative sign bit, then the magnitude is found by taking complement second complement of this number. So, that is your 0 we take complement 0 1 1 0 plus 1, that is your 0 1 1 0 1, and that is equivalent to 13. So, number becomes minus 13. So, now subtraction of second complement system. The subtraction option using the second complement system actually involve the operation of addition and really no difference from the previous cases. Virtually second complement will be brought it itself to convert from your subtraction to addition. So, when subtraction of one binary bit number, the subtrahend from the another binary number, that is minor, the following procedure is followed. So, negate the subtrahend, this will change the subtrahend to its equivalent value of opposite sign and add this to a minor. The result of this addition will be representing the difference between the subtrahend and minor. Example is here subtrahend 4 from 9. So, minor is plus 9. So, second complement form this minus 9 is your 0 1 0 0 1, and subtrahend plus 4 is in second form, it becomes 0 0 1 0 0, and now you have to negate find the second complement of subtrahend, that becomes your 1 1 0 0 plus 1, that is triple 1 0 0, the second complement of minus 4. So, we have a number here 9. So, 0 1 1 0 9 plus, and this for minus, this is second complement, with the sign. So, 1 0 0 1 1 0 0, and then now we add it all. So, it becomes your 1 0 1, then you have a again 0, and then 1 goes to here. So, it becomes 0, and then you have a again the carry, that is 1, you discard it. So, result becomes your 0 1 0 1 1, and that becomes plus 5. So, that is the way how we go. Very virtually we converted this, your you can call it the subtraction to addition by using this complement procedure like. So, now arithmetic overflow, consider the adding 9 plus 8. So, we have a 9 here, 0 1 0 0 1 and plus 8 0 1 0 0, and when we add it here. So, we have a typically a you can call carryover, and this becomes the incorrect sign, because that may be misled with the your negative sign. So, answer should be 17, but there the magnitude 17 require more than 4 bits. So, therefore, overflows into the sign bit position. The overflow condition can occur only when 2 positive or 2 negative numbers are being added, and it always produces an incorrect result. So, to overflow can be detected by checking if the sign bit of the result is different from the sign bit of the number being added. So, from this you can detect that there is a overflow. So, now coming to some of the problems, the theoretical problem. So, starting what is the total range of decimal value that can be represented in 8 bits. So, here we have a n equal to 8. So, thus we can represent decimal number from 0 to 2 to the power 8 minus 1, that is 255, and how many number bits are needed to represent the decimal value ranging from 0 to 12,500. With the 13 bit we can count from 0 to 2 to the power 13 minus 1, that is 8 1 9 1, but with 14 bit we can count 0 to 12 2 to the power 14 minus 1, that is 16,383. So, clearly 13 bits are not enough, but 14 bit will get up to 12,500. Thus, we require the 14 number of bits require 14 to represent the 12,500 number. So, how many hex digit can a nibble? 1. How many nibbles are in BCD digit? 1. So, what is the largest number that can be represented by using 8 bits? That is 1 2 to the power n minus 1, 2 to the power 8 minus 1, that is 255 10. So, that represent equivalent to. So, what is the next binary number following 1 0 0 0? So, you just add in sequence. So, that becomes 25 10, the next number is 26. So, that can be represented. Now, coming to typically exercise, list the advantage of digital technique. 3 advantages are easier to design, easier to store information, greater accuracy and precision, programmability, and less affected by noise and high degree of integration. List the 2 primary limitations of digital technique. 2 limitations are real world, physical quantity are analog, and digital programmation takes time. Then what is the largest decimal value that can be presented using 12 bits? That is 2 to the power 12 minus 1, that is 4095. So, what is the an advantage of encoding the decimal number into BCD rather than state binary? What is the disadvantage? Advantage ease of conversion, and disadvantage BCD require more bits. Now, coming to solved numerical problems. Now, starting for how many bits are there in the 1 byte? There are 8 bits in 1 byte. Convert the binary number 1001.0112 to decimal. So, just taking power from decimal here. So, it say 2 to the power 1 into 2 to the power 0, then 0 into 2 to the power 1 and 1 to the power 2 plus 0 to 2 to the power minus 1, then second bit is 1 minus 0 to the power minus 2, and then 1 into 10 to the power minus 2, and calculating equivalent decimal, that comes 5.375 at the base of 10. Convert this entire 1001 1010 11 11 0010 in by hexadecimal. So, you have to make the group of 4 this number, and then convert the 4 group comes 8, this comes equivalent to f, and this comes equivalent to 2. So, it becomes f2 at the base of hexadecimal. Now, add the 11.011 and 1110.11 to verify the converting the decimal. So, when you convert this you can add it, and when you convert equivalent to this, just adding, because adding goes very straight with the binary number, there is no problem. Represent minus 8 in second complementary representation. So, plus 8 is 0 1 1, you take first complement, it just interchange the bits. So, 0 become 1, 1 becomes 0, and 0 0 becomes 1 1, add the 1 to get the second complement. So, it becomes 1 0 0, double, that represents the minus 8, that is the second representation of second complement representation of minus 8. That is a, you can call it like a bit, that is minus and remaining is 8. So, the sixth example is the second complement form of a binary number is 10001. What is the number in decimal form? 1001, that is the original negative number. So, we have to have a first complement it to just change the bit, 1 becomes 0, 0 becomes 1 and 1 becomes 0. So, plus add 1, so it becomes 0 1 1 1 1 and that is plus 15, that is second complement of negative of original number, and therefore, your original number was 10001 was minus 15 at the base of 10. So, the second complement form of a binary number is 10000. What is the number in decimal form? This is a special case of second complement form, and this is 140, that is minus 2 to the power 4, that is minus 16. Subtract plus 4 and minus 4 in second complement. So, take the second complement of the subtrahend, that is your 01001 plus 9 to the produce the 1001, that is the, and add this minus to the second complement, that is minus 4, taking second complement of this. So, here we have a representation of minus 4 and this is a representation of minus 9, and then we add it, we have a discard 2 bit and this becomes minus 13. So, to find out answer, takes second complement and becomes 13. So, result have a sign bit 1. So, it is second complement form. Now, convert 3710 to binary. So, that method we already talked about. So, you can take the digital part of it. Okay. So, you can divide by 2, it becomes 90, then by 2 to 4.5. So, you have 1, then 2 0, then you have 1 0 and 0.5 1. So, you start from this typically 37 start from your typically your 100 at the base of 2, that is the equivalent representation of your 37. Now, example 10, the number is a 5 bit signed binary number and it is a complement in second complement and determine the decimal value of 11010. Answer is the sign of 11010 is 1. So, the number is negative. So, the magnitude of is unknown, find the magnitude of negating second complement, the number convert into positive. So, we convert first complement 1001, just change the digit. So, 1 1 becomes 0 and 0 become 1, 1 becomes 0 and 0 become 1, then we add 1. So, it becomes 0 0 1 1 0. It is a plus 6. So, because of the result of the negation is 0 1 1 0. So, plus 6, the original number 10001 must be equivalent to minus 6. Now, these are the unsolved problems, some of the unsolved problem here. I mean, you can just do in the same way as we discussed earlier, the solved problem, and these are the, of course, the references from which we developed this lecture, and thank you.